All right. First question on the assessment was, what is the probability of, if you've got your 10 numbered cards from 1 to 10, of getting a multiple of 4? So basically, first, we just have to start off with how many different outcomes could we get by drawing a card. 10 different cards, 10 different outcomes. So our bottom number is going to be the number of outcomes, which would be 10. Now we just need to figure out how many chances of getting, or how many times can we actually get a multiple of 4. Okay, so if we multiple of 4 is like counting by 4, so we'd go 4, 8, 12, 16, 20, and not all those numbers are in these cards, so we just have to figure out the ones that are. 4 is a multiple of 4, and 8 is a multiple of 4 as well. So we have 2 out of our 10 that's going to get us multiples of 4. Now that's something that we could do a few things with. We could find the percentage of this. I could just do 2 divide 10 on a calculator to figure out the percentage chance we have of multiples of 4. 2 divided by 10 is going to be, on a calculator, 0.2. Now it's not 2% because we got to circle 2 numbers here for the percent. So if we circle 2 numbers, we've got this empty number right there, which is going to be a 0, which is going to be 20%. Okay, so we have a 20% chance of getting multiples of 4. Now we can also go back up here and reduce this down. Something that goes into 2 and 10, 2 is the only thing. So if I reduce that down, I get 1 out of 5. So I have a 1 in 5 chance. Now if I figure out what that is, it should be the same thing. But on a calculator, if I do 1 divide 5, I do get the same thing. I get 0.2, which is going to be, the percentage would be the first 2 numbers, so I need to put another 0 in there. So it is going to be 20%. So you have a 2 out of 10 chance down to 1 out of 5, which is going to be 20%. All right, here we have a compound event. We've got 2 things going on here. We've got probability of getting an even number when I roll the dice. Then I need to flip a coin and get heads. So we've got to take these 2 events separately and then just multiply them together. So even number on a dice, 6 outcomes. The even numbers would be 2, 4, and 6. Okay, so that would be 3 even numbers. So 3 out of 6 chance getting an even number. Over here, getting heads on a coin, which would be 1 out of 2. 2 outcomes, heads or tails. You want the 1. Okay, we multiply this together, we are going to get 3 out of 12. 3 out of 12 chance. Okay, we can do some things with that. 3 out of 12 would be, divided by 3 would be 1 out of 4. So then we've got 3 out of 12 or 1 out of 4, which are equal, which are the same thing. Now, no matter which one of these I pick to find the percentage, top divided by bottom, 3 divided by 12 on a calculator, 1 divided by 4 on a calculator, it doesn't matter. We are going to get 0.25, which is 25%. So your chances of getting an even on a dice on a roll, and then next flipping a coin and getting heads, is 25%. In this question, we go back to a couple of important probability vocabulary words that we talked about probably in part 1, probably a little bit in part 2 as well. Theoretical probability and experimental probability. Okay, the 2 key words is basically we have theory, and theory basically just means what should happen. Okay, an example would be, in theory, the sun is going to come up every single day. Okay, it may not happen one of these days, but in theory, it's going to come up every single day. An experiment is what's actually going to happen. The key word is experiment in here. Okay, experimental probability says that this says it should come up every day. Maybe it won't. If we actually look, you never know. So in this case, if we get the probability of an odd number on a dice, okay, the theoretical probability of getting an odd number on a dice, where we've got choices of 1, 2, 3, 4, 5, and 6, odd numbers 1, 3, and 5. So theoretically, we are expecting to have a 3 out of 6 chance of getting odds on a dice. So meaning if I roll it 6 times, I should get 3 odd numbers. Or if I roll it, I mean, we can reduce this down. Divide by, what, 3? It would be 1 out of 2. If I roll it twice, I should get one odd number. Okay? Or maybe I take the 3 6 that I have here and I multiply it by any number, because equal fraction you can multiply by anything. Maybe I multiply by 4. 12 24s. Okay? Maybe I say out of 24 rolls I'd expect to get 12 odd numbers. Okay? That's good. That's a theoretical probability, or what should actually happen given the circumstances. Now the difference is the experimental probability. It is possible that I roll a dice 6 times and I don't get any odd numbers. It's possible that I roll a dice 6 times and I get all odd numbers. It's even possible for me to roll a dice 24 times and get all odd numbers. Roll a dice 24 times and get no odd numbers. So the difference between the two up here is what should happen. Okay, 3 out of 6. That's the probability we came up with because there are 3 odds out of 6. Definitely. Does it always happen that way? Experimental probability, when you actually run the experiment, no. So the answer to this question is, what is the theoretical probability of an odd number, rolling an odd number on a dice? And we would say 3 out of 6. You could reduce it down to 1/2. You could change that to a percentage. Hopefully everybody just knows that 1/2 is 50%. But if you don't, you can do 1 divided by 2, and you're going to get 0.5. We need the first two numbers for a percent. We have 1, but we're missing the other one, so we need that 0, so it's just 50%. In the last question, we need a tree diagram that shows how many different outfit combinations we have if we have 3 pairs of pants, 4 shirts, and 2 pairs of shoes. So I've started this out already. We're just going to start with the very first one on here, 3 pairs of pants. So I've got 3 branches drawn off, pants 1, pants 2, and pants 3. Okay? Now, for every pair of pants, we have 4 shirts to choose from. So I'm going to do that. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and I'm just going to put shirt 1, shirt 2, shirt 3, shirt 4, and so on. And I won't label the ones down here. You just got to know that's shirt 1, 2, 3, 4, shirt 1, 2, 3, 4. Okay. Now to finish this off, we just took care of the shirts. Now we need 2 shoes for each one. Okay. So 2 shoe choices, or 2 pairs of shoes choices. So here I'm going to have shoe 1, shoe 2. Shoe 1, shoe 2. Shoe 1, shoe 2, shoe 1, shoe 2. Down here I'm going to draw the lines, we're just not going to label them. We know we'd have 2 there, 2 there, 2 there, 2 there, 2, 2, 2, and 2. And now we need to know how many possible outfits we have. So altogether we just have to count the final branches. 1, 2, 3, 4, 5, 6, 7, 8. 8 more would be 16, and 8 more would be 24. So we have 24 possible combinations altogether. And if we read this diagram, let's say we took this one right here. Okay, to read that, I would be taking pants 3, let's see, following this path, which would be shirt 2, and then following this path would be shoes 1. Pants 3, shirt number 2, shoes number 1. If I followed this path right here, I'd be doing pants 1, shirts 4, shoes 2. We can also show this like our complex probabilities. I'm going to pick 1 out of 3 pairs of pants. I'm going to pick 1 out of 4 shirts. I'm going to pick 1 out of 2 pairs of shoes. Multiply these all together. All those would be 1. At the bottom it would be 12. 12 times 2 would be 24. Each one of these we pick is 1 out of 24 possible combinations. So your answer is 24 possible outcomes.